Today I am going to discuss the moment of inertia, that is Engineering Mechanics Module 4 Part 5 ESME 301. Now what is radius of gyration? So radius of gyration, that is the moment of inertia of an area about an axis divided by the cross-sectional area of the figure, gives the dimension of the length of the second power. This length is known as radius of gyration of the figure. So in this figure, that is figure 1, so there is the axis and A is the area, that is in the compressed form, in the strip form. So that area is at a distance k from the reference axis. Now kx is nothing but root over of IA and ky is nothing but root over of IA. Now this in general form, k is nothing but root over of I by a, so I equals to ak square. So this k is called the radius of gyration. Now moment of inertia of simple section. Suppose a rectangular section. So in this problem number 1, moment of inertia of a rectangular section. So this rectangular section moment of inertia we have to calculate. So in this figure 2, if you see this figure, there is a depth D and the width B, and the axis is passing through the centroid. So let us consider a small strip of thickness dy, that is at a distance y from the reference axis, that means the centroidal axis, xx axis. Now the area of that strip it is nothing but, so that is b into dy, that is the small rectangular strip area. Now the moment of inertia of the area of the elemental strip about the xx axis is nothing but distance square into area, that means y square into dA. Now the moment of inertia of the rectangular section about the xx axis, that means the total moment of inertia of this about the diameter, about the centroidal axis, that is xx axis, is nothing but ix equals to integration of y square dA, and the limit should be minus d by 2 to plus d by 2. Now putting the value of dA, so finally that is ix equals to nothing but b into y cube by 3, and putting the value of the limit minus d by 2 to plus d by 2, so finally bd cube by 12. Now similarly, if we calculate the moment of inertia in the case of about the y-axis, similarly if we consider an elemental strip dx at a distance x from the y-axis passing through the centroid, we have elemental area. So just like the previous discussion, so dA should be d into dx. So from this figure it is clear. So moment of inertia about y-axis, so Iy is nothing but minus b by 2 to plus b by 2, these two are the limit, into y square dA. Now putting the value of dA in here, and finally Iy should be integration minus b by 2 to plus b by 2 x square dx, and finally Iy should be db cube by 12. Now to find the moment of inertia of the rectangular section about the base AD, that means the lowermost line AD. So consider same strip, you have to consider an elemental strip dy at a distance y from the AD, that is moment of inertia with respect to the base, that is you can write IAD equals to 0 to d y square dA. So these are the limit, 0 the lower limit and d is the upper limit. So finally IAD should be bd cube by 3. So we observe that the moment of inertia of a plane area is varying with the position of the axis. So to define the moment of inertia of a plane area, it is necessary to mention the axis about which we want to find the moment of inertia. Now in the problem number 2, if we see this, then you have to calculate the moment of inertia of a circular section. So in this circular section, the diameter of the circular section is d, that means radius is r. So in this figure, that is shown in the figure 5. So consider an elemental element at a distance r from the center O. So radial with the being dr and bound by radii theta and theta plus d theta. So obviously the area of the element should be dA equals to r d theta into dr. Now moment of inertia about the diametral axis, that means the x axis, that should be Ix equals to nothing but integration y square dA. Now Ix, there are two variables, so that's why there will be the double integration 0 to r and 0 to 2 pi. So r sine square r sine theta square into r d theta into dr. So first you have to integrate the first integration and finally the second integration. So the finally that is equals to 0 that is pi into 0 to r cube into dr. So pi r to the power 4 by r. If the diameter is d, in that case in terms of diameter, so Ix should be pi into dy to the power 4 divided by 4. So pi d to the power 4 by 64. Now the circle is symmetry about x-axis and as well as y-axis. That's why Ix equals to Iy should be pi d to the power 4 by 64. Now in this case, that is the problem 3, that is moment of inertia of a triangular section. In the case of triangular section, it is shown in the figure 6. So the height is h and base is b. So same just like the previous problem, we have to consider an elemental strip that is at a distance y from the base, and that is the dy is the thickness. So first you have to calculate the width of the strip. So from the similar triangle, so ACB and DCE, these two triangles are similar. So from the similar triangle, we have to calculate the width of the DE base of the new formed triangle, that is HY by H into B. Now the moment of the elementary strip about AB axis, that is y square into dA. Now putting the value of dA. Now the moment of inertia of the triangular section about the base AB, that is IAB equals to nothing but the limit, we have to put the limit, that is 0 to h. So y square into h minus y by h into b dy. So just after integration we will get the value of IAB, that is bh cube by 12. That is the moment of inertia of the triangular area with respect to the axis AB. Now set up standard table. So this, if you see this table, that is there is rectangle, triangle and circle. In the case of rectangular area, if we consider the axis, that is the centroidal axis, that means x dash and y dash. In that case, Ix dash should be the moment of inertia about the x dash axis, that is bh cube by 12, where h is the height and b is the width. Similarly, y dash, that is bh cube by 12 also. So b cube, that is b cube h by 12. And similarly, I bar x and I bar y is nothing but bh cube by 3 and b cube h by 3. And jc, that is polar moment of inertia, that should be bh by 12 into b square plus h square. In the case of second diagram, that is the triangle, that is in case of x dash axis, so I bar x dash, that is nothing but bh cube by 36, and Ix, that is the lowermost line, that is with respect to base, that is bh cube by 12. In the case of circular area, where r is the radius, in this case Ix and Iy, that means these two are same. So that is pi r to the power 4 by 4, and j, that is pi r to the power 4 by 2. In the case problem number 4, determine the moment of inertia of a L section as shown in the figure. So, and it also, we have to calculate the centroidal axis parallel to the legs. Also we have to find out the polar moment of inertia. So in this L section, so first off we have to calculate the momentum, the centroidal position, that is x bar and y bar. That is, first you have to divide the total area into two sectors, that is sector 1 and sector 2. That is the lowermost beam, that is sector 1, and the that is wave portion, that is the sector 2. Now just divided the two parts, that is, and the value of x bar and y bar should be 6.44 and y bar should be 8.05 centimeter. Now coordinate of the centroid with respect to the centroidal axis xx and yy, that is C1, that is 3.56 and 5.55, and C2, that is 4.44 and 6.95. Now Ix should be the moment of inertia of the rectangle 1 about xx axis and moment of inertia of rectangle 2 about xx axis. So finally if we put these two values, and we will get the Ix should be 9819.45 centimeter to the power 4. Similarly Iy should be that is putting this value, that is 5 into 22 cube by 12 and plus 100 into 3.56 square, and we will get the Iy should be 6284.45 centimeter to the power 4. Now the polar moment of inertia, that is Iz, is nothing but Ix plus Iy. So Iz should be 10103.9 centimeter to the power 4. In the problem number 5, determine the moment of inertia of the section as shown in the figure 8 about the centroidal axis perpendicular to the wave. So in this case also we have to apply the parallel axis theorem. So there are three sections, section 1, 2 and 3, that is, and we just divide the total I section into three parts. So first again we have to calculate the centroidal position. So this figure is symmetry about the x-axis, so position of the centroid will lying on the y-axis. So y bar we have to first calculate. So total area should be divided into three parts, so 1, 2 and 3. So we have the value of y bar should be, that is 5.5 centimeter. Now moment of inertia of the section 1, so Ig plus A1 y1 bar c square plus Ig2 plus A2 y2 c square and Ig3 plus A3 y3 square. So that is this moment of inertia of section 1. So in section 1, that value is 4586.67 centimeter to the power 4. Let the axis xx passing through C and perpendicular to the wave of the given section by parallel axis theorem. So I11, that is Ix plus A y bar square, where A equals to A1 plus A2 plus A3, that is 80 centimeter squared. Now Ix equals to I11 minus A y bar square. So finally Ix equals to 2166.67 centimeter to the power 4. Thank you very much.